All right, problem of the day 19 is looking at identifying the difference between SN1 and SN2. So let's start with our first one. We've got an electrophile right there at the red dot. Is that primary, secondary, or tertiary? Primary. Does primary indicate that it's SN1 or SN2 usually? SN2. So if we think about this, the nucleophile is going to do our backside attack on our electrophile and kick off our leaving group, which means it's going to be on this face, and our CH3 group is going up, our deuterium is going down, and our hydrogen is going back. So you can draw this a variety of different ways. You could draw it right side up, left side down, however you want. But the key is that this product should have that inversion of stereochemistry, right? We go through that trigonal planar transition state and we flip the stereochemistry. So in this case, your product should have an R stereocenter in it. Is there a potential of forming an enantiomer with an SN2 reaction? Do we get a mixture of products? No, we only get one product with an SN2 reaction, and we only get the inverted product. All right, the next one, if we look at our electrophile, is that primary, secondary, or tertiary? Primary. Does that favor SN1 or SN2? SN2. So in this case, we did it this way. We'll do our backside attack, kick off our bromine. Are we attacking a stereocenter? No, so we're not going to invert the stereochemistry because there is no stereochemistry there. We're not really overly concerned about it. So if we draw in our final product, looks like that. And then what about this stereocenter right here? Did we do anything to it? No, so it's just kind of hanging out. We can draw our product in like that. Are we going to deal with an enantiomer? No, because it's SN2, not SN1. We're not going to deal with any mixtures. All right, the next one is an electrophile, but what sort of electrophile is it? Tertiary. That carbon's attached to 3 other carbons, so it's tertiary. That favors SN1. So SN1, if you remember, your leaving group falls off first. Let me draw that more clearly. And we've got our carbocation here. And then our lone pair on our oxygen can add in through the top or the bottom, but does it really matter? No, we're not dealing with a stereocenter again. So in this case, we get the same product regardless of what face we attack. And then, we're not quite done yet. Let me even rewrite this a little bit clearer. The very last step is usually a proton transfer, and if you drew this as being protonated, I'll still give you full credit. But that oxygen right here has a positive charge. It's not very happy. It wants anything to deprotonate it. So in this case, this is actually an equilibrium reaction. But traditionally, people, when they're drawing substitution reactions, like to draw neutral products, not products that have charges. So we've got an OCH3 and our final product. And in this case, we're not dealing with enantiomers because we're not making a mixture of products. So I always tell you guys that you can write plus enantiomer to save you some time, but don't always assume that there will be enantiomers. It really depends on whether or not that center that you're attacking is a stereocenter or not, and it depends on whether or not you're looking at an SN1 or SN2 reaction. All right, 3 examples of aprotic solvents. This was kind of freebie points. If you looked them up, you got credit. I don't like that students remember an alphabet soup of acronyms. I want you guys to know the bond line structures. So here's a couple of them that show up frequently. This is acetone. This is DMSO. That's dimethyl sulfoxide. We've got this one with the carbon-nitrogen triple bond. What's this called? Acetonitrile. Were there any other ones? DMF. All right. So DMF looks like this. Another one we had was THF, which looks like this. It's an ether. And there are a handful of others that you may run into in the textbook. But what's the key feature with polar aprotic solvents? Cannot hydrogen bond. And we're going to continue talking about solvents today, but this is a really powerful tool that we have in our disposal, is the fact that we can use a polar solvent that cannot hydrogen bond. So let's go back and talk about solvents. So yesterday we ended by talking about the different pathways for SN1 versus SN2. We said with SN2 we go through a polar transition state. Same with SN1. And we finished by saying that both are stabilized in polar solvents. The question is, when would you use polar protic and when would you use polar aprotic solvents? So let's consider this. Protic versus polar aprotic. And I'm going to draw these as generic ions. So I've got an ion here that's negative, and I've got an ion here that's negative. And what's a good hydrogen bonding solvent that we could use? Water. Universal solvent. So let's assume we've got this in water. The hydrogens are really attracted to that ion, right? Because hydrogens have a partial positive, and that ion's got a full negative. So we run into a situation where in polar protic solvents, the ion is highly stabilized through the hydrogen bonds that are surrounding it, right? Let's consider an aprotic solvent. Let's pick acetone. So acetone's pretty easy to think about. All right, can the anion on the right be stabilized as much? No, there's a dipole, but dipoles aren't as strong as H bonds, right? So if we think about this, we can say, all right, in polar protic solvents, the ion, or anion I should say, is more tightly solvated due to H bonds. Another way of thinking about this is you can say it's more stable, right? It's wrapped up by the shell of hydrogen bonding that's stabilizing the anion in solution. All right, so now if we think about both of these, the one on the left versus the one on the right, which anion is going to be more nucleophilic, the one on the left or the one on the right? The one on the right is going to be more nucleophilic. So if we think about this, this one's less stable anion. Therefore, it is more nucleophilic. All right, so if we're thinking about an SN1 versus SN2 reaction, which reaction do we want a really strong nucleophile? SN1 or SN2? SN2. So if we think about it, polar aprotic is best for SN2 since Nu strength is important. So now we've got a really valuable tool. If we want to drive an SN2 reaction over an SN1 reaction, we want to choose the appropriate solvent for that reaction to be performed in. Another way of thinking about this is with an energy landscape. So let's make an energy landscape. Where we've got energy here, we've got a reaction here. So let's say our nucleophile and protic solvent is with black, and it has some activation energy to go to our product. With the polar aprotic solvent, essentially what we're doing is we are destabilizing the starting energy of our nucleophile, right? It's less stable, and it's still going to go through a pretty similar transition state, but we're going to go down here. Let me clean this up a bit. So if we think about this, polar aprotic solvents destabilize the NU, or nucleophile, and lower the activation energy. Nucleophilic attack is all about lowering activation energy, right? So by destabilizing our nucleophile, we're going to lower that activation energy required for that reaction. Does that make sense? It's a little bit weird to think about, but let's go through and make kind of a summary sheet. We're going to do a couple of these. So let's compare nucleophilic atoms in the same column for aprotic solvents.
Could you go back to the...
Scroll up.
Yeah.
There you go.
A little more.
One more.
Yeah. What is the reaction between the right side and the negative charge?
So there's going to be a dipole ion interaction, which is less stabilizing than an H bond ion interaction. So if you remember back to general chemistry, ions are really, really stable in hydrogen bonding solvents. They're less stable in polar solvents, and even less stable in nonpolar solvents. So the question is, why don't we use nonpolar solvents if we want an SN2 reaction? It's a very practical question. Can you dissolve salt in oil? No. So it's just a solubility issue for that point. So it's kind of this nice middle ground we can hit where we're destabilizing our nucleophile, but we're still allowing it to dissolve in solution. Okay, so let's compare some nucleophilic atoms that are in the same column. And so I'm going to make a list. We've got fluoride, chloride, bromide, and iodide. These are all in the halogen column, right? They're all potential nucleophiles. Which one do you think is going to be most nucleophilic? Fluoride, chloride, bromide, or iodide? Remember, nucleophilicity has a lot to do with stability. Which one's least stable? Fluoride. So if we look at this, we can say, all right, fluoride is less stable. That means it's more nucleophilic in aprotic solvents. This is closely related to basicity. And which one's the most basic? Fluoride, chloride, bromide, or iodide? Fluoride. So again, iodide's really, really stable as an anion because it's so big. That means it's not super interested in getting its proton back. Fluoride, on the other hand, is really, really small. That means it's less stable with that negative charge. It's more reactive. And so we can also look at this as being more basic. So we've got similar trends in aprotic solvents that we do with acid-base reactions. So now the question is, when would we ever use protic solvents? So let's address that. So when would we use protic solvents? Does anybody have an idea? What do you think?
Well, like if you got a lot of steric hindrance going on, like a tertiary carbon.
Okay, so maybe with the tertiary carbon, what sort of reactions do we perform at a tertiary carbon? SN1. So do you guys remember back on that flow chart? Or not flow chart, that sheet we were working on the other day, the decision-making sheet? If we look at our nucleophile, we said with an SN2 reaction, we really, really need a strong, unstable nucleophile that isn't bulky. With an SN1 reaction, nucleophile strength doesn't really matter. So maybe a polar protic solvent would work okay in an SN1 reaction where it wouldn't work in an SN2 reaction. So let's go back to our solvent choice, and let's make a note of that. So, so it can be used with SN1 since nucleophile strength isn't, oh my goodness, come on Microsoft, work with me here. User error. Could be a little bit of both. Since nucleophile strength isn't as important. Nope. All right, so let's do another comparison. Let's consider the following. And I'm going to do two separate ions in a polar protic solvent. The first one I'm going to look at is SH minus. And we're going to compare this to hydroxide, which is OH minus. And again, let's compare this in a polar protic solvent. So I'm going to draw out a bunch of water around it. Let me move this in a little bit. We'll do the same thing over here. All right, so if we think about this, is there hydrogen bonding occurring in both of these, or only one? They can both H bond. We've got water in both. We've got H bond stabilization in both of these. So let's draw in our little H bonds to our ions. So in each of these, we're being stabilized by ions. So we can say, all right, they're both tightly stabilized or solvated. So meaning they're really, really wrapped up in the solvent around them. So we can't really compare the relative stability based on solvation anymore. So now we've just got to backtrack it a little bit, and we've got to look at sulfur versus oxygen. Which one of these do you think is going to be more tightly solvated based on size? Exactly. So they're both tightly solvated, but oxygen is smaller, and therefore it is a little more tightly solvated. You can think of this as a surface area to volume ratio, right? If you're smaller, you've got a really high surface area to volume ratio, which means you're going to interact with the outside world a lot more, right? If you've got a really large surface area to volume ratio, you're not going to interact with the outside world to the same degree, right? You have a question, Johnny?
How is H-bond? How is that an H-bond between nitrogen and sulfur?
So you can have an H-bond interaction between a negative charge, but the important thing to remember is for an H bond to occur, you have to have a hydrogen coming off the phone, fluorine, oxygen, or nitrogen, and a lone pair. So in this case, we've got a lone pair on sulfur, and we've got a lone pair on oxygen. So you have to have an H bond donor, the thing that's donating the hydrogen, and an acceptor, which is a lone pair. So both of these are stabilized through H bonding. Does that make sense? Okay.
So the SH is the nucleophile state?
Well, let's do that. Let's compare them. Based on this argument where we're saying that oxygen is smaller and more tightly solvated, do you think it's going to be as accessible for a nucleophilic attack or less accessible? Less accessible. So we can go through and we can say, all right, oxygen is less available for a nucleophilic attack. Therefore, SH minus is the better nucleophile. Okay, so let's make another list again, just like we did before with fluoride, chloride, bromide, iodide. But let's do this for a different column in the periodic table. So here, let me make sure I'm writing it the same way. Comparing nucleophilic atoms in the same column. In the same column, but this time we're dealing with protic solvents instead of aprotic solvents. And so let's compare OH minus to SH minus to SEH minus. Which one's going to be most nucleophilic? Yeah, the selenium. So selenium's pretty darn big. It's going to make an excellent nucleophile. It also explains why selenium is often very, very toxic too. So if we go down the column now, we're becoming more nucleophilic. Because it's less tightly solvated. So the biggest mistake people make in first term organic is they think that nucleophile strength is directly related to base strength. But if you remember back to our base strength, which one's the better base, hydroxide or selenium? Hydroxide. So if we go up a column, it's more basic. So it's not fair to say that because something's more basic, it's going to be the better nucleophile. It is in aprotic solvents, but it is not true in protic solvents.
So does that trend relate to every column periodic table?
Yes, as long as you're going up and down a column. We're pretty lucky as organic chemists because we only deal with that very top right-hand corner. We don't really look at the metals in the left-hand side too much. So as far as we're concerned, it applies to our entire periodic table. Yeah. Yep.
So since it's bigger, wouldn't it have more surface area to interact with other hydrogen bonds, or am I thinking about that wrong?
We're more looking at surface area to volume ratio. So things that are really, really small have a huge surface area to volume ratio. So if you think about them, they're interacting with their outside world to a greater degree relative to their size than a really large spread out atom. A really large spread out atom with a huge atomic radius has a pretty small surface area to volume ratio. It's more easily polarized. Yep.
I was just wondering if you could go up a little bit.
Sure. Right there?
Yeah, that's
Too
too much.
much? You want me to go down?
You can just change it. Okay, I'm done.
All right. So if you've noticed, we're using nucleophiles that are negatively charged. Do you have a question?
Yeah, I'm just wondering, can we use the solvent to figure out if the secondary carbon is going to be SN1 or SN2?
Yes, we're going to get there.
Oh, okay.
Yeah, it's almost like I paid you to say that. But let's continue on. We're comparing nucleophilic atoms in the same column under protic solvents. But now let's stop and think about things that aren't anions. What if we just have something that's neutral? If you guys remember that last one on the problem of the day, it was just in methanol. I didn't give you an anion. And the methanol did a nucleophilic attack. So now we have to look at, what about neutral nucleophiles? Meaning non-anionic. So let's go through and compare two. Let's compare ethanol, everybody's favorite alcohol, CH2, CH3, to thioethane. What's going to be the nucleophilic site on each of these? There's no negative charge. Lone pairs. There's lone pairs on both of them. Lone pairs can be nucleophiles, right? All right, so now we need to think about these lone pairs, and we need to ask ourselves, which one is going to be more available to attack? The larger one, meaning the sulfur, or the smaller atom, meaning the oxygen? Oh, this is tricky. So think about which one's going to pack more tightly, the large one or the small one? The small one's going to pack really tightly. We just talked about surface area to volume ratios. We said that small atoms tend to interact with their surroundings a lot more than really large diffuse atoms. So if we look at this, we can say, all right, sulfur is larger. It packs less tightly because it's got that larger surface area to volume ratio. Therefore, do you think it's going to be a better nucleophile or a worse nucleophile? Better nucleophile. Because it's more available for attack. I'll just write better NU. All right, so now what we need to think about is, all right, in an SN1 reaction, you guys saw that we could use a neutral nucleophile. Why would I use this nucleophile rather than sulfur with a negative charge on it? What do you think?
Well, sulfur had a negative charge. It's in a proton thing that's it would just bond with like hydrogen.
Yeah, it could hydrogen bond, but if you think about it, this is less nucleophilic, right? It doesn't have a negative charge. We said it doesn't really matter in an SN1 reaction how strong our nucleophile is. A weak nucleophile will work. But think about it if you're a chemist. Is it a lot easier to mix a solvent, a salt, and your electrophile, or just a solvent and your electrophile? It's a lot easier just to mix two things than three things, right? Same thing's true when you're purifying your reaction. If you have a 3-component mixture, it's a lot harder to purify than a 2-component mixture. So oftentimes it just comes down to practicality. So let's make a note on this. So often our solvent is our nucleophile for SN1 reactions. It's easier. All right, as you guys saw in that last problem of the day problem, what's the one caveat if we're doing this in our reaction? What was the last step? Deprotonation. So let's make a note. So the last step, and shoot. Come on. Scroll down. Note, last step, proton transfer. All right. Now I know this can be super duper overwhelming, but let's make a trend table and try to sort all of these trends out because so far we've seen a handful of trends. All right. Since we're organic chemists, we're dealing with carbon, nitrogen, oxygen, fluorine. If we go down, we've got chlorine, bromine, iodine, sulfur, selenium. Let's throw in phosphorus for good measure. We've got our top right-hand corner of our periodic table, right? All right, let's make a little list. And we've got polar protic. Oops, sorry. Let me redo this. Polar aprotic plus an anion. So in this case, we're putting our nucleophile into a polar aprotic solvent. Are we getting more nucleophilic as we go right to left or left to right? This goes back to yesterday's. What's going to be less stable, a carbon with a negative charge or a fluorine with a negative charge? Carbon. So we can go through and we can say, all right, left to right, this is more nucleophilic. Right? That's assuming we're looking at carbon with a negative charge versus fluorine with a negative charge, right? So polar aprotic gets more nucleophilic as we go right to left across a row. All right, what about with a column? Do we get more nucleophilic as we go up a column or down a column? Up a column. So in polar aprotic solvents, we're again looking at just stability. So we would go, all right, up here we've got more nucleophilic. Let me actually put it over here just so we're keeping it clear. All right, now let's look at the counterpart. What if we use polar protic? Plus an anion. What if we're going across the row, not up and down a column? What's going to be less stable across a row, chlorine or fluorine? It's actually the exact same trend for polar protic. So if we're comparing across a row, we would say, all right, both of these get more nucleophilic the less electronegative your atom is. The flip-flopped one is when we're looking at the columns, right? So what do you notice about the polar protic plus an anion with the columns? Does it get more nucleophilic as we go up or down? Down. So we can go, all right, this is more nucleophilic as we go down a column. All right, and then what about polar protic that's neutral? Do the trends stay the same as our green arrows, or do they differ at all? Yeah, they typically stay the same. And I drew it as green, so if you're being clever, you can say, oh, he's stuck with green right there. So these are our general trends. The one thing that people get hung up on is the fact that these are flip-flopped depending on what solvent they're in, right? So polar protic versus aprotic can be a little bit tricky. All right, so now let's go back to our summary sheet. And we're going to tackle our solvent right now. So SN2, what sort of solvent do we prefer for an SN2 reaction? Do we want polar protic, polar aprotic, non-polar aprotic? So polar aprotic. And what about SN1? Polar protic. And the other thing to note with an SN1 is that our nucleophile is often solvent. All right, so we're almost done with our flow chart. We still have to tackle our leaving group problem and how to anticipate leaving groups. And I'll let you guys know leaving groups are a lot easier to assess. But before we go on and we do that, I've got a video I wanted to show you guys. Oops. Let me make sure I can pull this up. Some people were asking me, is there any better way to visually look at SN1 versus SN2, and the answer is yes. So let's take a look at an SN2 reaction. If it'll open. See if TCC's internet is up to par here.
Where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blown inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released.
I smell an Oscar. All right, let's quickly switch over to the second one. And I posted this on the class notebook too, so if you are stuck visualizing these, you can pull up the video on the class notebook and take a look at it.
Tertiary halogenalkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenalkanes, the small hydrogen atoms in primary halogenalkanes are replaced by bulkier alkyl groups. The bulky alkyl groups do not allow attacking species to approach the central carbon atom. Consider the reaction between 2-methyl 2-bromopropane and a hydroxide ion. It has a two-step enthalpy
So now we see our two-step camel hump.
The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion.
All right, I'll stop it there as much as we want to listen to the whole thing. But if you guys have trouble visualizing this, the videos are really helpful. We don't have class tomorrow, but when we come back on Thursday, we're going to finish up on leaving groups and do a big in-class activity.
When's the next test?
Our next test is the Tuesday before Thanksgiving.